Hello everybody, my name is Ilham Naharuddin Shah. Welcome to this video on the control strategies in heating and cooling networks. The goal of this video is to get you acquainted with the most important control tasks in heating and cooling networks and how we can use control technology to operate and optimize the performance of district heating and cooling networks. In heating and cooling networks, we use the classical controls to handle the basic tasks of steering and stabilizing the grid by controlling key physical quantities such as pressures, temperatures, or mass flow rate. On the other hand, advanced control is used to optimize the system performance by controlling the thermal energy storage and building temperature to reduce or sieve the peak load. For this purpose, we need an optimization-based control systems such as model predictive controllers, usually abbreviated as MPC. First of all, let's talk about the classical control system. To begin, consider a district heating grid with a generation plant, a thermal energy storage tank, three houses, a simple pipeline, and a return pipeline. Typically, there are 6 control systems in this network: 2 temperature control systems, 3 pressure control systems, and a demand control systems at each house. The first classical control systems is pressure controls that consists of differential minimum and maximum pressure control. The differential pressure controls is used to maintain the pressure difference between the supply and return pipe by adjusting the control valve near the network pump. We also have minimum and maximum pressure controls that are responsible for keeping the pressure levels within the acceptable range to prevent cavitations or pressure overpressures. Now let's move to the temperature controls. In a district heating network, we have supply temperature control systems. The supply temperature control systems ensures that the supply temperature reach the predefined set point value. In a district heating network, the supply temperature is adjusted by heating carrier fluid and adjusting its flow rate using a pump. Besides supply temperatures, we also have minimum supply temperature controls. This controller is necessary when the heating demand is low, such as during summer season. The last classical control system in demand-side control system. The demand-side control systems is responsible for ensuring customers' comfort by maintaining the room temperatures by adjusting the heating valve and pumps according to thermostat sensors reading. The future heating and cooling networks require more sophisticated control systems to face 2 important challenges. The first challenge is related to the heat production efficiency. We are interested in minimizing the generation costs and CO2 emissions. To address this challenge, we need a control system with performance optimization capability. The second challenge is related to the adoptions of more renewable energy sources. Renewable sources such as geothermals typically have limited capacity and lower generation temperatures compared to conventional sources such as coal-fired boilers. In this case, we need a controller that can account for operational limitations. For addressing this challenge, an optimization-based controller such as MPC is the most suitable control framework. To better understand the working mechanism of the optimization-based controls, let's consider the following scenario, namely generation cost minimizations with MPC. To achieve this objective, we produce some energy and charge storage tank when the electricity price is low, and discharge them when there is heat demand and the electricity price is high. With this strategy, we can avoid the usage of fossil-fired peak boilers. In this setting, our objective is to minimize total generation costs. We have some constraints such as temperatures, pressure, flow rate charging limitations, and task limitation. The control signal or decision is the charging and discharging amount of storage tank at each timestamp. In this case, our flexibility source or systems is thermal energy storage tank. After setting up our target with the MPC framework, we formulate an optimization problem over a certain period. The decision or control signals is chosen by solving the optimization problems. As an illustration, suppose at time step k, we observe how each feasible solution may affect the total cost over 4 hours. This observations or prediction process is encoded in the optimization problem. Subsequently, we choose the best decision over the prediction horizon among the feasible decisions by solving the optimization problem. While we have the decision over 4 hours, we only implement the decision for the next time step. After all variables are updated and the impact of our current decision is evaluated, we repeat the entire process. MPC has some advantages. Thanks to the optimization features, the resulting control signal or decision will optimize the objective while respecting the operational limitation or constraint. Due to trajectory prediction features, we can avoid the short-term trap. As you can see in the figure, some decision might lead to a trajectory with lower at a certain time step. However, by making longer predictions, we can see that the decision leads to higher costs. Finally, by repeatedly implementing the decisions and updated parameters, we can account for the unforeseen variables such as the resulting decisions is robust toward disturbance or uncertainty. Now, let's wrap up our discussions. In this video, we have discussed the control strategies in heating and cooling networks. We learned how classical control systems help drive and maintain the controlled quantities of heating and cooling components. We also learned how the optimization-based controllers is useful for exploiting the flexibility sources to optimize the network performance. Both controllers are critical tools to realize next generation heating or cooling networks.